In this video paper we present an approach of electricity grid forecasting of power consumed and produced of photovoltaic, PV, prosumers. We will present an Ensemble machine learning algorithm combined with Facebook's open source profit forecasting. Let's get some disclaimers out the way. This project was undertaken based off an ongoing Kaggle competition presented by Enefit, one of the largest energy companies in the Baltic region. This body of work is the work of Dr. Michael Treasure, and it will not be submitted to the Kaggle competition for many reasons, 3 of which are: 1. The extensive computing requirements of this body of work will not meet the competition requirements. 2. The work is being carried out with a broader research goal in mind. 3. The competition is still ongoing, and the work presented here is to put forward a machine learning approach quite likely different from any other approaches the competition will see. However, given the competition's rules, the data will not be shared outside representations in tables, graphs, etc. as presented in this body of work. Who are prosumers? A basic definition is that a prosumer is someone and/or an entity that produces electricity from green energy sources for their consumption and then sells the excess energy produced to the national electricity grid. In this body of work, we will concentrate solely on solar power, photovoltaic, i.e., PV, as the green energy source. Understanding the fundamental problem. We all are aware that predicting the weather is a science fraught with the uncertainties of the elements of nature. Based on research, the power output of solar power generating systems has been observed to change, up or down, by as much as 70% within the span of 1 minute. Additionally, this may differ by more than 75% from 1 hour to the next. These fluctuations in the power output of PV systems cause imbalances in the power grid. If they are not managed by balancing reserves, these fluctuations will affect the operating frequency and local voltage of the entire grid network. Therefore, to limit the occurrences of imbalances and lower the need for carbon-intensive, inefficient and costly reserves, adequate scheduling of PV power supply and demand is essential. The market is still in search of an optimal solution. To date, there exist many PV predictive models, but according to Enefit, the solutions they have seen so far have proven to be not good enough due to their low forecast accuracy. Enefit's position is that, and I believe most other national grid power generators that are embracing green energy as power sources for their grid supply would attest to, the underlying problems with PV predictive models on the market today lie in their inability to accurately account for the wide range of variables that influences prosumers' behaviors. It is therefore imperative that a better solution be found that has a greater PV power predictive accuracy, that when adopted, may materially help to reduce the imbalance and associated costs to the national grid. So, what type of data is needed to more accurately predict and forecast PV generation and consumption by prosumers? Based on the data provided by Enefit and supported by the extensive research carried out by Dr. Treasure, there are at least 4 buckets of features needed. Bucket 1. Historical weather features. In this bucket, there are about 15 features thought of. The emphasis here is on thought of, as important to a predictive model. Some of these features include historical data on temperature, dew point, rain, cloud cover, high, low, medium, and total. GPS coordinates, lat, long. Solar radiation, direct and surface. Wind, speed and direction. And dates of occurrences of the features as mentioned in this bucket. Bucket 2. In this bucket there are features related to the following: gas, client, and electricity. Some of these categories of features include gas prices, low and high prices. Electricity, low and high prices. client, relating to installed capacity, county, consumption type, customer type, and dates of occurrences of the features as mentioned in this bucket. Bucket 3. Forecast weather features. Similar to the historical weather features bucket, for this bucket, there are about 14 features thought of, and again, the emphasis here is on thought of, as important to a predictive model. Some of these features include forecast data on temperature, dew point, rain, cloud cover, high, low, medium, and total, GPS coordinates, lat, long, solar radiation, direct and surface, wind, speed and direction, and dates of occurrences of the features as mentioned in this bucket. Bucket 4. Target features. These sets of features are what one would typically need for a supervised learning algorithm to target its model towards. These feature sets are generally established by business rules, strategies, and goals and generally are revised as frequently as needed. Some of the features included in this bucket of features for forecasting include data on target for power needs, county, prediction unit, product type, consumption type, and dates of occurrences of the features as mentioned in this bucket. Now let's shift focus to the methodology used in developing the machine learning forecasting model being presented here. Much of this body of work is carried out using PySpark, which enables one to perform real-time, large-scale data processing in a distributed environment, PySpark, using the Python programming language. Earlier we discussed the 4 buckets of data sets. Now we will talk about the set of tasks in our methodology. Task set 1. We load the different datasets, clients, historical weather, forecast weather, gas prices and electricity prices. Task set 2. We perform initial exploratory data analysis, EDA, coupled with extract, transform and load, ETL, processes. These initial processes are quite extensive and include cleaning the datasets, visualization of the data for understanding the underlying data, joining and creating subsets of the joins as are necessary to minimize the need to handle, from a compute requirement, exploded datasets. Task set 3. Once we are satisfied that we have cleaned and have usable datasets that are castable into data frames, we prepare the data frames for our first machine learning pipeline process. The purpose of this first machine learning pipeline, a regression process, is to perform feature engineering, a process we will talk about later. Task set 4. Here we combine the output of our first machine learning pipeline with the trained dataset discussed previously. Task set 5. In this set of tasks, we perform more EDA and ETL processes similar to what we did in the second set of tasks earlier. Task set 6. Now with a combined data frame, we divide this data frame into training and testing data frames for our second machine learning pipeline random forest regression process. This is the heart of our machine learning model solution. The training data is piped into a random forest regression model. We then use the model on the test training dataset from which we get our prediction layer. Task set 7. In this set of tasks, we perform yet more sets of EDA and ETL processes, not unlike what we did in the second and fifth sets of tasks earlier. Task set 8. Here we take a two-prong fork approach. One prong of the fork, we use Facebook's profit forecasting tool. On the other prong of the fork, we use another PySpark machine learning pipeline. Later we will go into discussions as to what Facebook's profit forecasting tool is and why we include it as part of our solution set. The PySpark machine learning pipeline model use here is a classification model, and the use of this will also be discussed later. Task set 9. Here we address our decision process and the metrics used to assess whether our approach does deliver a better predictive model than those available today. Task sets 10 and 11. Here we present a deep learning alternative and will discuss later why a deep learning approach was not a good solution path. Let's take a visual glance at some of the source datasets from across the Estonia region in which the data was collected. In the first set of the charts, we see 5 sets of distributions of PV produced and consumed across the 15 counties of the Estonia region. In the second set of the charts, we see 2 distributions of customer types, is business, or is not business, for the PV produced and consumed across the Estonia region. In the third set of the charts, we see 4 distributions corresponding to the 4 product types for the PV produced and consumed across the Estonia region. In the fourth set of the charts, we see 2 distributions of consumption type, is consumption, or is not consumption, for the PV produced and consumed. And in the fifth and final set of the charts, we see 1 distribution of the desired total target power produced and consumed across the Estonia region. Earlier on, we mentioned that we would return to the subject of feature engineering. Here, we explain the basic mathematics behind our machine learning regression feature engineering model. Recall from earlier we identified 5 buckets of features with aggregate input features count of 54. These 54 features were fed into our model and the ML process produced a multilinear regression function resulting in the following equation. Y hat MVLR equals AA1, times x1 plus AA2, times x2 plus AA3, times x3 plus AAN, times xn, where n turns out to be 13. Therefore what this employed machine learning model did for us was to whittle down 54 features to 13 features with the greatest correlated impact to determining our desired target values. Later, in this presentation, we will talk more about some of these 13 features and why other features were not directly shown as highly correlated. However, please take a moment to observe the code output, showing the 54 features input and the 13 features output. Let's talk more about multivariate linear regression and our feature reduction process. Multivariate linear regression, MVLR, is simple, but widely applied in machine learning models for solar forecasting. The machine learning MVLR model forecast the solar power output by considering a linear relationship between a matrix, Y, of n, predictors, and t, timestamps, and the power output y hat MVLR, a vector of regression coefficients beta, which we represent in equation 1 as follows. Y hat MVLR equals beta times y plus epsilon. In this case, epsilon measures the uncertainty that lies with the regression model. The coefficients are found by minimizing, min, the differences between the actual power value, y, and the predicted y hat MVLR power output. We calculate min, shown in equation 2 as follows. Min equals y minus y hat MVLR. A variation to the linear regression model shown in equation 1 is the least absolute shrinkage and selection operator, LSO, model. Essentially with LSO the number of included input variables is reduced by application of a penalty to coefficients of some variables that have a minor contribution to the target and in effect reduces these to a zero coefficient. This is represented in equation 3 as shown here. This third equation basically provides the mathematical explanation of how we were able to reduce 54 predictor features, i.e., variables, to 13. Putting the mathematical theory in practical perspective. As these next set of graphs will show. Intuitively, one would think temperature would be a dominant predictor feature in our predicting equation. However, this wasn't so. The power of the machine learning multivariate, Lasso regression model, is to use correlation between features to technically achieve principal component reduction. For example, as you may see from these next set of graphs, the predictor, dew point, is correlated with the predictor temperature, and importantly, the timestamps predictors capture temperatures. Therefore, the Lasso model technically considered the predictor, temperature, as having a zero coefficient relative to the target. Temperature, being correlated with timestamps and dew point, is therefore represented within these coefficients. Timestamps here represent time in the past for the weather events that occurred and time in the future, based on weather forecast. These two additional graphs shows temperature and snowfall over past and forecasted times. You may discern from the graphs that temperature rises and falls based on time of year corresponding to the changing seasons. Therefore, visually, one may conclude that date is good indicator of temperature in the context of our model. These types of correlations are picked up from the data through the power of the machine learning process. Similar explanations may be made for other variables that are showing a zero coefficient. In this regard, note that the prices of gas and electricity are not showing as directly correlated factors to our target. These next two graphs provide more visual explanation in understanding why the machine learning model, evidenced by the coefficients shown earlier, has cloud cover and radiation as key influence predictor features. Cloud cover, all levels, and radiation, all levels, matters in our predicted value outcomes against our target values, for electricity produced, and consumed, by PV prosumers. Regardless of the season of the year, the presence or absence of cloud cover will impact the temperature levels a solar panel experience. The red area in the first chart shows the total cloud cover for the period for which the source data was provided. The green area is mild cloud cover coverage. The second chart shows different levels of surface radiation for the period. The dominant red area of the chart is the forecasted downward surface radiation. The green area of this chart shows the forecasted direct solar radiation. Previously, we explained in detail our feature engineering process, where we used a multivariate linear regression machine learning approach to give us a predictor equation. We now have to ask, how confident should we be that we have gotten a good and usable base model to move forward with to our next phase? Is there enough evidence and are there metrics that we can use to substantiate our conclusion here? In this frame, we will take a physical evidence check on the predicted data frame, to find support for our conclusion. Here, we show a table of 25 rows from our output prediction data frame. The table shows 25 predicted values, while Lasso, against the target, y, values. Recall the equation shown here that we discussed earlier, where min equals y minus y, Lasso, with beta being the sum of the coefficient, and we add a penalty factor, constrained by some hyperparameter value h. In practical terms, here is how we relate it to our own outcome as shown in the highlighted area of the table. In the case shown here, the penalty and hyperparameter applied is already accounted for. If we look at row 1, for example, we calculate min 1 as follows. 52.794 minus 52.981. This gives us the absolute value difference, that we term, error, between our predicted value and the actual target. The goal would be for our model to produce values of min as close to 0 as possible, without overfitting. Therefore, a visual inspection of the 25 rows suggests that we do have a good outcome from our feature engineering process. Supporting our visual inspection are at least 4 relevant metrics. Based on these 4 metrics, our machine learning feature engineering process can be deemed successful. We have been able to whittle down 54 predictor features to 13. The coefficient of determination R squared is 99.99%. It should be noted that an R squared percentage close to 100% is desirable. The root mean squared error, RMSE, is 0.6206. The mean squared error, MSE, is 0.3851. The mean absolute error, MAE, is 0.4406. For the RMSE, MSE and MAE, the lower these are, the better the model performance. In our case, these values are very low, relative to the wide range of our target PV values, which indicates good performance of the model. Therefore, all these metrics support our earlier visuals of having a good featured engineered model to move forward with. The prediction data frame, which is the output from our feature engineering process, will now provide the construct for our forecasting. This machine learning linear regression feature engineering process is part of the overall solution approach we are delivering, as a more accurate forecast model than many of the forecast models that are on the market today. Moving to the next phase of forecast model development. Given we now have a developed classical multivariate regression model, why not stop here? At least 2 major deficiencies have to be addressed. 1. Classical multivariate regression models do not generally handle time series data well. 2. They also tend to overfit, meaning they can be too perfect on training data, but not good on tests, i.e., unseen data. We did split our initial data set into train and test sets, nevertheless, the inherent deficiencies should not be ignored. Therefore, the next phase of our model development is to address these potential deficiencies. Let's address the first deficiency, that of time series data. What is the profit forecasting tool and why do we use it here? Profit is an analysis tool and is a procedure for forecasting time series data. We use it here for at least 3 reasons. 1. It provides a helicopter view of the temporal nature of our data. 2. It is relatively good at easily identifying multiple different seasonal periods in the data. Therefore, visualizing daily, weekly, and yearly seasonality in the data is relatively easy. 3. The feature engineering approach we adopted does not inherently impact Profit's ability as an analysis tool, and as a procedure in forecasting time sequence data. Given the strengths of Profit, why not use it solely for our forecasting solution? There are at least 2 reasons for this. 1. It is a documented fact that Profit provides subpar predictive performance in a great deal of scenarios. 2. Profit is not ideally suited to handling multivariate dependent features. It does provide for a regressor approach in overcoming some of this, but in general it is limited, especially in handling vector-assembled features. Here we compare Profit's forecast distribution with the distribution of the target. Recall, the target is the power produced and consumed by prosumers and is independently set by the company, Enefit in this case. Profit's forecast model is based on the input from our feature engineering process of using multivariate linear regression. This input is the predicted values from the machine learning process we discussed earlier. In this frame, we compare two output models from profit with that of the target distribution. One profit model is without regressors, and the other is with using two regressors. Product type and county. There is hardly a noticeable difference between the two profit distributions, which means the regressors add little to no value change. However, the two profit forecast distributions compares extremely well to that of the target. In this frame we can more clearly see profit's strength in being able to identify seasonality in the data. The first chart shows profit's temporal long-term forecast of prosumers' electricity consumption and production. The y-axis is the range of electricity and the x-axis is the time horizon. The diverging shaded area to the right of the graph is the projected window profit gives for yet unseen data range. Notice, the electricity level hovers around the 200 kWh mark, but diverge positively to a high of about 1,200, and negatively, to a low of about a negative 200 in the shaded area. The relative straight line at the 200 kWh level on the y-axis, between around August 2021 and July 2023, shows profit's weakness in performance accuracy. However, the second and third charts do show the power of profit to model well the weekly and daily trends in the data. It is remarkable the ability of profit to use our baseline ML predicted values to capture the daily highs and day-of-week changes in the photovoltaic electricity produced and consumed. In this frame, this first chart shows the breakout of the winter season's distributions in the data. And the second set of charts show the corresponding winter season weekly and daily trends. Two distinct winter periods are shown. Winter of December 2021 to March 2022 and winter of December 2022 to March of 2023. For both winters, we see a clear flooring at around the 2,500 kWh for electricity consumed and produced. We can also see periods within these winter seasons, where the electricity produced and consumed have changing peaks, to a high of above 15,000 kWh. It is clear also that electricity produced and consumed is higher at all levels in the 2022 to 2023 winter season, than the 2021 to 2022 winter season. This frame shows profits modeling seasonality for the summer period based on the data. These summer charts show the breakout of the summer season distribution, and the corresponding summer season weekly and daily trends. The data only covered one full summer for the period June 2022 to September 2022. One will observe that the distribution of the electricity produced and consumed during the summer is quite different to the winter seasons we earlier looked at. Particularly, the peaks of the summer are different from the winter seasons in terms of total electricity for the season, day of the week and time of day. The daily peak was on a Tuesday during the winter seasons, but for the summer season, the daily peak was for the period between Thursdays and Fridays. This next frame shows profits modeling seasonality for the fall periods based on the data. These charts we next show here gives the breakout of the fall season's distribution, and the corresponding fall season's weekly and daily trends. Two distinct fall periods are shown. Fall of October 2021 to December 2021, and fall of October 2022 to December of 2022. Again, you may observe that the distribution of the electricity produced and consumed during the fall is quite different to the winter and summer seasons we earlier looked at. The peaks of the fall are different from the winter and summer seasons in terms of total electricity for the season, day of the week and time of day. The daily peaks for the fall season was on a Wednesday, different from both the summer and winter seasons. It may also be observed that the electricity produced and consumed is higher at all levels in the 2021 fall season than the 2022 fall season. In this next frame we see profits modeling seasonality for the spring periods based on the data. These next charts show the breakout of the spring season's distribution, and the corresponding spring season's weekly and daily trends. Similar to the winter and fall, there are two distinct spring periods as shown here. Spring of April, 2022 to June, 2022, and Spring of April, 2023 to June of 2023. Again, observe the differentiation in the distribution of the electricity produced and consumed during the spring, from those of the fall, winter, and summer seasons. The peaks of the spring season have their own uniqueness in terms of total electricity for the season, day of the week and time of day. The daily peaks for the spring seasons were on Tuesdays, but were almost as high on Fridays. Finally, it may again be observed that the electricity produced and consumed is higher in the 2023 spring season than the 2022 spring season. We now shift focus to the third phase of our forecast model development. Thus far, we have used 1. The classical multivariate linear regression machine learning model for feature engineering, giving us the opportunity to focus on the features that are mostly important to our forecast outcome. 2. The profit forecasting tool, to primarily address one of the two deficiencies of the classical multivariate linear regression model. In this third phase of our model solution development, we will employ the random forest machine learning linear regression model. In doing so, we should note three things. 1. It does not inherently address the temporal nature of our data, but we used profit to have addressed this issue. 2. It does, however, help us to address the overfitting problem much better than the classical linear regression model. 3. It has the ability to capture much better the nonlinearity and data complexity. In our case, the data is quite complex and does have a wide range. Therefore, let us now go into our random forest multivariate linear regression model development, to help us to address the second deficiency in our process thus far, that we mentioned earlier. What is random forest machine learning? Random forest is an often used machine learning algorithm, which combines, that is, bags, the output of multiple decision trees to reach a single result. It is a supervised machine learning algorithm. It can be used for both regression and classification problems, which we will do in this body of work. At its core, random forest works by randomly creating equally divided decision tree samples of training data, with replacement, meaning each item may be chosen more than once. Random forest is inherently nonlinear, but is quite accurate and flexible. It is based on an ensemble learning process, integrating multiple classifiers to solve complex problems. Let's further explain the how of random forest in our model development. We start with the classical machine learning multivariate linear regression output. Recall, this output was our prediction, reflecting the important correlating features necessary to make predictions towards our target values. We then combine this multivariate linear regression output with a vector-assembled process, with additional features from our Enefit trained dataset. This trained dataset contains the business operating goals and objectives set by Enefit. Next, we configure the machine learning algorithm parameters to effect a random forest process to handle a new linear regression. Then, we trigger the random forest machine learning algorithm to assemble decision trees for processing through a series of steps, that is, the depths of the forest. At each depth, the majority vote is captured and fed to the next depth. This process continues until a final decision is made. You will observe that in our random forest model, we employed 100 trees, a depth of 8 with bins of 32. And we are taking the linear prediction from our earlier linear regression as label column for our random forest, meaning we are supervising the random forest ML model with data from this to produce new prediction of its own, which you see in the code as RFL features. Let's examine our random forest multivariate linear regression results. You may observe in this frame, in terms of metrics, at least the following. 1. We calculated the mean absolute square, MAAE, for two separate scenarios. The first scenario, we evaluated against the classical linear regression predicted input, as the label column. And in the second scenario, we evaluated against the target, as label column as well. The MAAE for both were practically equal at 50.87776 and 50.94847 respectively. 2. We calculated the R² similar to how we used the MAAE with the two different scenarios. The first scenario, we evaluated against the classical linear regression predicted input, as the label column. And in the second scenario, we evaluated against the target, as label column as well. And both R² values were practically the same at 87.94%. We did these two sets of scenario calculations as a sanity check, to assess how well our feature engineering linear regression predicted values would stack up against the trained data set, as was independently provided by Enefit. The results of the comparison does show that the metrics on both fronts were practically equal, thus giving us confidence that our approach to this point is quite solid. I should remind us at this time that the Kaggle competition is still ongoing, therefore the input data from Enefit may change between this presentation and the closing of the competition. However, as of this presentation, and based on the data set we have used, our MAAE score is the best so far, compared to those revealed on Kaggle's competition site. Let us now compare our machine learning random forest forecast model distribution with the models from the target and profit distributions. From these next displayed charts, we can see that our random forest linear regression distribution is strikingly similar to the ones we examined earlier for the target and profit distributions. The first chart shows the distribution of the target values, and I will remind you again that the target values are those set by Enefit. The second and third charts are those from our profit forecasting tool, and shows profits predicted distributions without regressors, and with regressors. The fourth chart provides a comparison of the predicted values distributions from both our classical linear regression and our random forest regression models. We observe that the random forest linear regression distribution, shown as the color green in this fourth chart, addresses the overfit deficiency of the classical regression model distribution, shown as the color green in this fourth chart. Again, based on these visuals, we can continue to be fairly confident in our model development process. We will next look at seasonality from our random forest perspective. Addressing the seasonality in the data with our random forest regression model. Looking at these next four charts, we observe the random forest regression output distribution for spring, summer, fall and winter seasons, for the PV electricity consumed and produced by prosumers. The first chart shows the distribution of the predicted average values for the spring seasons. The second chart shows the distribution of the predicted average values for the summer season. The third chart shows the distribution for the fall seasons. And the fourth chart shows the distribution for the winter seasons. We observe that from season to season, the distributions are different. The peak average values are different. The average peaking clusters are different. Therefore, while the random forest regression model doesn't directly capture the seasonality trending, as the profit forecasting tool does, one can still observe the seasonal variation in average PV electricity consumed and produced by prosumers. The complexity in the data was easily handled with our random forest linear regression model, and it did address our earlier overfitting problem. Phase 4. Our overall objective in this project was to put forward a solution path to developing a more accurate predictive modeling solution for electricity produced and consumed by prosumers, with an emphasis on photovoltaic prosumer types. Our solution path entailed a hybrid machine learning algorithm approach. In Phase 1, we developed a classical multivariate linear regression machine learning model for our feature engineering process. In Phase 2, we used the predicted output from Phase 1 to feed into the profit forecasting tool to address the time series nature of the data. In Phase 3, we developed a random forest multivariate regression machine learning model to achieve our ultimate prediction model against our business-provided target values. In this final Phase 4, we shift focus to employing a random forest classification machine learning model to address binary questions in decision-making around our predictions and forecast. For example, there are questions such as: is the customer a business type or not? Is the prediction is consumption or not? In making these binary classical decisions and to understand the degree of confidence supporting the decisions, we will now employ a random forest classification model. For one of our random forest models, we presented the question, is consumption 0? That is, we asked the machine learning process to give us the outcome on the question. Is the electricity prediction for a prosumer consumption, which it will answer with binary representation 1? Or is the electricity prediction for a prosumer production, which it will answer with the binary representation 0? Here in this chart, we show 10 classification predicted records, ranked by highest probability outcomes for prosumer electricity produced. Our random forest classification machine learning model shows an overall accuracy of 82.096%. In the table, please take a moment to look at column 4, which is the predicted binary classification of our model. Then take a look at the column 6 of the table. Column 6 is the trained value from our target data set as provided by Enefit. Given the accuracy and our visual confirmation, it means we have a fairly good confidence limit in our model to address the classification question of is PV electricity for consumption or not by the prosumer. In this frame we also show a comparison for the predicted values for our classical linear regression and random forest linear regression with our target values. With the developed process now in place, this random forest classification model may also be used for addressing other binary decisions by simply changing out the label column in our model as appropriate. This Phase 4 of employing a random forest machine learning model now completes our predicting and forecasting solution set to more accurately forecast electricity consumed and produced by PV prosumers. Let's summarize and conclude. In this body of work, we developed and demonstrated an ensemble machine learning algorithm and profit forecasting approach. We believe it may be used to more accurately predict and forecast electricity produced and consumed by PV prosumers. We acknowledge that our solution put forward here may have its limitations. We further acknowledge there could be more feature engineering and parameter tuning done to improve results and/or address gaps. In this presentation, we did not address the deep learning path as a validation process, but will do so in a follow-up presentation. However, this body of work and the solution put forward presents a viable alternative to other solutions that have to date been applied. This work was the work of Dr. Michael Treasure.